Learn like a pro.
All right, let's talk about velocity time graphs. Now, these things, they're so much more than just lines on a grid. They are, in fact, the complete story of an object's motion. And my goal here is that by the end of this, you'll be able to read them like a pro. So let's just jump right in.
So you look at a graph like this, and yeah, at first glance, it might just seem like a jumble of random jagged lines, right? But believe me, every single piece of this graph is telling a story. It tells us how fast something's going, what direction it's moving in, and how that motion is changing second by second. So let's break down how to read this story together.
And here's the best part. The key to cracking this whole thing, it just boils down to two. That's it. Just two simple but super powerful rules. Once you get these down, you'll be able to tackle pretty much any velocity time graph that comes your way.
Okay, power rule number 1. It is all about the gradient, the steepness of the line. That gradient is the acceleration. Think about it. A super steep line means the velocity is changing really fast. A shallow, gentle slope, that's a slow, gradual change. And what about a line that's perfectly flat, perfectly horizontal? Well, that's a slope of 0, which means, you guessed it, 0 acceleration. It's that simple. The slope tells the story of the acceleration.
And now for our second power rule. This one is all about the space, the area that's trapped between our graph line and that horizontal time axis. That area, believe it or not, gives you the object's displacement. And displacement is just the fancy physics way of saying how far it's ended up from where it started. So, if the area is above the axis, it's moving forward. If the area dips below, it's moving backward.
All right, so there you have it. Our two core rules. Gradient is acceleration and area is displacement. Got it? Good. Now let's see what happens when we apply these rules to the different kinds of lines you're going to see on these graphs.
Okay, let's kick things off with the easiest one to spot, a perfectly horizontal line. What's the gradient of a flat line? It's 0, right? So our first rule tells us the acceleration has to be 0, and that means the object is just cruising along at a nice, steady, constant velocity. But what if that flat line is sitting right on the time axis? Well, that means the velocity is 0, so the object is just standing still.
Now, what if we see a straight line, but it's sloped? Well, since the slope of a straight line never changes, it's constant. That means the acceleration is also constant. We call this uniform acceleration. It means the object's velocity is changing by the exact same amount every single second. It's either speeding up or slowing down, but at a perfectly predictable, steady rate.
Okay, but what about a curved line? Now this is where things get really interesting. See, with a curve, the slope isn't constant anymore. It's changing from moment to moment. And if the slope is changing, that means the acceleration is changing. A classic example, a skydiver. When they first jump, they're accelerating pretty consistently. But as air resistance kicks in and builds up, their acceleration starts to decrease. That change, that's what a curve on a VT graph shows.
All right, let's put that second rule of ours to work. We're going to figure out an object's total displacement. And the best part? You don't need any calculus or crazy advanced math. It's basically a little geometry hack.
Yeah, seriously, no calculus needed. All you have to do is look at the area under the graph and break it down into simple shapes you already know. Rectangles, triangles, maybe a trapezoid. Then you just calculate the area for each of those simple shapes, add them all together, and boom, that's your total displacement. So for the journey you're looking at here, it comes out to a clean 20 meters.
Okay, time to level up. We need to talk about a really crucial idea that unlocks the full power of these graphs, and that's the difference between speed and velocity. It all comes down to one simple word: direction.
So, that horizontal time axis, the line where velocity is 0, you need to think of that as a dividing line, a real boundary. Anything on the graph that's above that line means the velocity is positive. Let's just call that moving forward. And any part of the graph that dips below that line, that means the velocity is negative, so it's moving backward. And this is key. The negative sign doesn't mean it's slowing down. It just tells you the direction of travel.
And that right there is the fundamental difference. See, speed is what we call a scalar. It only cares about how fast. That's it. So a speed time graph is always positive. It can never go below that 0 line. But velocity is a vector. It tells you two things: how fast and in what direction. And that's why a velocity time graph is so powerful. It can go into negative territory to show you that the object is turned around and is heading back.
Let's make this super clear with an example. Imagine you throw a ball straight up into the air. It goes up, then comes back down, right? The total distance it traveled might be, say, 50 meters. But what's its final displacement? Well, it's 0. because it landed right back where it started. A velocity graph shows this perfectly. You'd see a positive velocity as it goes up, and then a negative velocity as it comes down. The positive area under the graph gets completely canceled out by the negative area. It's a perfect picture of the journey.
All right, it's time to put all our new tools to the test. We're going to look at a complete journey, represented by a single graph, and pull out all the important information.
So check this out. This graph shows the journey of a train, and you can clearly see three distinct parts to its trip. First, from point O to P, we see a straight, sloped line. What does that mean? Constant acceleration. Then, from P to Q, it flattens out. That's our constant velocity phase, just cruising along. And finally, from Q to R, it's a straight, downward slope, which means it's decelerating at a constant rate until it comes to a complete stop.
And now, using just our two rules, we can figure out pretty much everything we need to know. Here's what we're going to do. First, we'll calculate the acceleration from the slope. Second, we'll find the total displacement by adding up the area under each of those three sections. And third, we'll use that information to find the average velocity for the entire journey.
Okay, the numbers are in. So first up, the acceleration during that initial takeoff phase was 2 meters per second squared. Next, the total displacement. We get that by adding the area of the first triangle, that big rectangle in the middle, and the final triangle, and that gives us a grand total of 2,200 meters. And with that, we can calculate the average velocity for the whole trip, which comes out to 29.3 meters per second. How cool is that? All of that precise data just from reading the lines and shapes on a graph.
So let's just do a super quick recap of everything. This right here is your quick reference guide, your toolkit for kinematics. The two big takeaways: gradient tells you acceleration, area tells you displacement. Just take a second, let that sink in. This little matrix has everything you need to decode the story of motion. So from now on, when you see a velocity time graph, don't just see lines, see the story. Remember this: you read the lines to know the speed, you read the slopes to know the acceleration, and you read the shapes to know the distance. Now you have the tools. What stories of motion are you going to uncover?